Hello, everybody. This is a special off-the-books, non-joy of coding video. It's Mike Conley here. I just wanted to show you something pretty cool that I don't think is w I don't think what I'm about to show you is often shown to people, or if it is, it's like this is like a black art that not a lot of people who hack on Firefox, I think, know how to do. So I wanted to show it off and maybe help other people see what's going on whenever I'm doing what I'm doing. So let me explain what's going on. Basically, I'm investigating a Talos regression, and that's for the tpaint test. That's whenever that's a test that runs where it will, like, the test will click on a link in content which will open a pop-up window, and then we measure the time between clicking on the link or causing, I don't think it actually clicks the link, I think it like calls window open, but it measures the time between first calling window open and the Moz after paint event firing in the content of the newly open window. So it measures the delta between those 2 points in time, and it does it like 20 times, and that's the test. And we take longer with E10S, and I don't know why yet. And one of the best ways of figuring out what's going on with a Talos regression is to gather a profile, and I've been able to tease a profile out of our try machines. There's a bug on like making that easier. I've got some patches. Where is it? Bug 1182595, where hopefully this is something that will be very simple in the future. Maybe we can even automate this whenever Talos regressions get filed, or we can just get profiles for people and do comparisons. But basically, I have two profiles, performance profiles, which, if you don't know, Gecko has a built-in sampling profiler, which is basically a way for it to write down what it's doing every couple of milliseconds. In this case, it's, I believe, every 10 milliseconds, Gecko will say where it is in the stack, and that way you can more or less measure, or you can get a sense of what the process is doing at any given time. And not just the main process, we can also look at what the content process is doing and what the compositor thread is doing at the same time. And that's really good for figuring out what's slow, because otherwise we'd just be guessing. And I wanted to show you me looking at these profiles. So I've got in this tab, this one is from the E10S Talos run, where this is just a single instance of a window opening and then closing. And you'll notice that like each of these little dark lines represents basically a sampling window, and the height of the line represents how deep the call stack was whenever we took the sample. So it's not like a measure of like how long it takes. It's a measure of how deep we are in the stack. And the color, it's not really apparent maybe, but there's like a slightly different color over here. This is slightly more red. And what that means is how long it's been, like the redness of each of these lines represents how long it's been since we've returned to the main event loop. So the redder it gets, it means that we're basically hanging if we start turning red. So so that's good. And so this is the non-E10S profile, and you can tell that because the content samples are not here. There is no content process for non-E10S. And here's the thing: if we drag across this range, we can see that this is a single instance of the window opening and closing. That's what these samples are for. And if we look at this window of time, it's 268 milliseconds, because that's what this is. This is a timeline. This took 268 milliseconds for non-E10S, and for E10S, if we do the same thing, this took 333 milliseconds. So we've accurately captured the regression, I think, in these profiles, and that's good because sometimes it's not always such a slam dunk. You'll capture profiles from something that reports a Talos regression, but for some reason it looks like the test takes longer in the case where like the test is performing better, and we have fewer samples in the test where, or in the case where, you know, the test is performing worse, and it's very confusing. But this one looks like kind of a slam dunk. I'm putting in air quotes. You can't really see me. I haven't hooked up my camera, but I'm putting slam dunk in air quotes because it more or less is playing by the rules that you would expect, where the slower one is taking longer to complete the test. And now we can try and figure out why. I have my suspicions based on just looking at this graph, but let's actually do the investigation. So the first thing that this test does is it opens a window, and opening a window has some cost. And what I'm going to do is take a look at what the cost is of actually constructing a Zool window and a native window and stuff in the single process case, because that gives us sort of a baseline for what we should be aiming for in terms of opening window costs. So what I'm looking at down here is the call tree. This is basically it's not like in order. It's telling me what the most expensive, like, it's kind of, I wouldn't call myself like a super expert in these profiles, but here's my interpretation. The number on the far left over here represents how many samples were taken at a particular, like, with something on the stack. Like how many times the startup XRE main frame was on the stack. Well, 268. So like we were always in the main loop is what that's saying. So that's not very useful. But there, as you go deeper and deeper, you'll find that there are something, and like whenever you have something highlighted down here, these turn green. That means that like this was on the stack in all of these samples up here. So I'm going to keep drilling down, and what I'm looking for is whenever we actually open a window, and that happens right here in Window Watcher. Like we go through all of this junk to actually convert the window.open call into something that causes an open. So it's basically here. I mean, like this calls this, calls this, calls this, calls this, which actually starts opening window. So this costs to open a window about 160 milliseconds, and that's the majority of the test is us doing the open. So that's what we need to remember. NS Global Window Open takes about 160 milliseconds, because I'm pretty sure the sampling rate was 1 millisecond per sample. So that's 160 samples, so approximately 160 milliseconds. So now if we switch, and I got that information over here, just so you know. And then over here for the E10S case, let's see if we can find the same thing, the call to open the window. And that will occur in the parent process, because the content is going to send a message to the parent to actually open the window. So there's sort of the same stack. So yeah, here we see it's actually taking slightly less time, 149 milliseconds to actually open the window in the parent process. So that's interesting. So that actually occurs more quickly in the E10S case. So that's good. There's potential for a win here, but we're doing other things. Like all of the things that are not green right now, that are not highlighted, are the trouble spots, is my guess. And you'll also notice that down here in the content process, if I were to select this this histogram down here, I have this big like red line, and there's a turtle, and then another red line and a turtle. And these are decorations to indicate that the content process is waiting on a synchronous message. The content process has sent a message to the parent, and it's blocked. It's just kind of like polling, waiting for that message to come back, for a response to come back. And there's two of them. There's one here, and this one's not unusual. This is the one where the content process has said, okay, I need a new NSI DOM window. Parent, please open me one. In the meantime, my caller really needs this right away, so I'm going to block until you've sent me the DOM window back. So that's not wholly unexpected. So we send a message to do the open window. The child waits for that window to get opened in the parent, and then the parent will send the DOM window, well, basically the tab parent thing back down to the child, which will convert it into a tab child, and then the tab child will get resolved into an NSI DOM window, and we'll return that to the caller. And then we stop blocking. And so you can see that, like, if I select this, we're doing this thing called PR wait condition var, pthread condition wait, where we're just waiting. We're waiting for that message to come back. And meanwhile, the parent is like opening this window up here. We're making window stuff happen. We're maybe drawing the window. There's lots of stuff going on. Yeah, there's drawing the window. all sorts of operations take place that are not unexpected. It's the other stuff that we're interested in. So let's take a look at some of this other stuff that's going on. So the first thing that happens is that we force the initial browser to be remote. That's new. That's not a thing that single process has to care about. That's not too expensive. That takes only 2 milliseconds, or 2 samples. So I think that's small potatoes. That's no big deal. We're looking for like 50 to 100 milliseconds worth of difference here, I think. Something like that. So looking down here, we can see, what are we doing? I've got some JS on the stack. We're getting some kind of security UI information. We've constructed the browser. We're in the browser XBL constructor. So this is us like actually. So we're still inside forcing initial browser remote. That's interesting. So maybe this is taking longer than I thought. We need that first browser to be remote. And so we're waiting. You know what? I don't think that's adding too much still. That's 5 milliseconds. That's not so bad. Now we're painting, because I can see paint, press shell paint on the stack. We do a couple paints. We can see up here, the graphics layer is informing us when certain things are happening. Like there's a display list update, a rasterization, a vsync occurs here, and then I believe this is a composite. So like there are various graphics operations. There's a reflow happens here. In this case, oh, that's interesting. Customizable UI internal insert widget. So the window is starting to like build its stuff. It's inserting widgets and whatnot in order to build the window. And that's interesting. Like maybe. So what's this? This is just us. We're processing next thread. Yeah, what's this? On process. We're notifying that the window moved. We dispatch a Chrome event. And then we tell the tab parent that it's updated its position. And then we're asking the platform, we're asking Linux, GTK basically in this case, for the screen bounds. That's interesting. I wonder if we do the same thing for single process. Get screen bounds. Do we do something like that? Now, over here I can filter. I can say get screen bounds, and it will filter out all the samples that don't have that. So yes, we do that, and that takes how many samples? I see 1 sample here, but in the E10S case, it takes 8 samples. So that's interesting. It takes a bit longer for the E10S case to get the screen bounds. That's very interesting. And we do it a little bit over here as well. So that's a neat bit of information. Oh, and like there's NS window get screen bounds. There's one here and there's one here. So there's like 2 different calls on the stack for getting the screen bounds. And both of them end up polling. In this case, this one is being called by, let's see, on configure event. Like, I think we're spending maybe too much time trying to get the screen bounds. The frame loader attempts to get the window dimensions, and then the window itself is getting the screen bounds, and you know the system is taking a while to tell us. So that's interesting. Now where are we? On location change in the browser places. That doesn't take too long. Remote web so this is also E10S specific. So the remote web process manager has received an async message. Some kind of progress update has occurred whenever we attempt to, when we first open the page. First it's on location change, then on state change, and then on security change, because the content has been loaded. The content for the content that is basically taking, so like the tpaint test. Let me show you the source for the tpaint test. Where is it? Tpaint, 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 tpaint. The tpaint test opens a window using this data URI basically, and this data URI adds an event listener for Moz after paint, and then as soon as it sees that event, it like removes the event listener and then tells the opener that the child was opened, and that's whenever we take another timestamp and do the delta, and then we close the window. So when that stuff is loading, we actually send messages from the child to change, like to say that, yo, the location's changed to this data URI, the state changed, the security's changed. So that's interesting. We'd probably do the same thing in single process as well. On location change. How long does that take? So we've got 8 samples. On location change apparently takes 4 milliseconds, or 4 samples. And over here it's taking slightly longer, but only 2 milliseconds longer. So maybe this isn't so bad. Let's see, what else have we got in here? Oh, we do it again. We've got more samples for the Web Progress Manager. Or, yeah. The prototype has call listeners. We're running on location change. Is it possible that we're running it like way more than we're supposed to? Like maybe twice? Maybe we're calling it twice. On location change and on state change. That's interesting. In this case, we're receiving, we receive the message here and we call progress listeners. And then in the other case, we're just running some script. I don't know why this would be called again, but that's worth looking into. So I'm going to write that down. So investigate whether or not we're sending, we're running the on location change, or the M tab progress listener thingies too many times. So that's one thing. That might be smallish potatoes, but that's worth looking into. I had another one as well, and that was like the get screen bounds might be taking too much time. And then what else? So we do a flush here. We have to do a composite. Now, I have another theory, and I said that at the very beginning, and I've actually already, if you looked at my notes, I wrote something down. I have something down here about try to ensure that the browser init sync message is sent at a time when the parent is idle. And that's because down here in the content process, we have this second like sync message where we're just waiting. And that sync message is in the browser child script where we send a message to the parent and we just hold off. And that message is like whenever the browser child script, which is loaded for every remote browser, when it starts up, at the very bottom of the script, we send the sync message to the parent saying, I'm starting up. And we send the outer window ID, and we are getting some like initial data back from the parent. And this sync message is blocking the Moz after paint event from being consumed by the script. Like this has to run first, and this will wait. This will block. And the Moz after paint that the data URI in the tpaint test is waiting for will not be consumed while we're waiting for this. So there's this like huge block of time here of how many milliseconds? Of like 31 milliseconds where we're just waiting. So what are we waiting for? Well, if we're waiting for the parent, it's because the parent is probably blocked. It's doing something else and it doesn't have time to service our like sync message request. And what's the parent doing up here um, whenever we're asking for this stuff? So I've clicked some samples up in here, and the one thing I can see it doing is that we are running some JavaScript. Specifically, what are we doing? We're running delayed startup. We're running delayed startup at the time that, like, delayed startup is this other event, is an event, not an event, it's a function that runs in the browser window as soon as it's finished painting. As soon as the browser window element has finished painting itself, then we run this delayed startup thing and we do like all this other stuff. Now that we were done painting, we do all this other sort of startup-y things. And that way we can try and paint the window as fast as possible and then do all the heavy stuff after. But it's possible that with multi-process Firefox, because we don't have to wait for the content process, like we've kind of shifted some chairs around on the deck of the ship, where the content process is doing its own thing, like it's taking care of constructing the dock shell and all of this business for the new window that's being opened. And so in the parent, the Moz after paint fires earlier, and so it starts handling that stuff and doing the delayed startup right around the time that the child decides to ask for that initialization stuff, and the parent's too busy. And so the child is blocked waiting for that information, and then as soon as it gets it, well, now it does some extra processing, and then it will like service the Moz after paint event, and then we'll stop the stopwatch. So this is the big one for me, that I think we might want to either get rid of the sync message, like send the newly created window information down in the message that comes down here. Like whatever this is waiting for, send it down with this first message, so that we don't have to wait twice in a row. And that, I think, will help. The other alternative is to just make sure that if this is sending a sync message, like if this sync message is really, really necessary, then have us make sure that the parent is as free as possible at that time. And that's of the two solutions, I think that's my least favorite. I'd rather just get rid of the sync message entirely. And then what else is the child doing while we wait, after we're done waiting? Is we do some JS, we interpret some JS, a pop-up blocking script is being run, whether or not we want to block the window that's been opened, I think, maybe. What else is being run? Again, this like on security change stuff. Over here we do a reflow. We're doing a flush of the layout. Do a reflow. And then down here we're waiting again. What are we waiting for? We're polling texture create for drawing. I think we've received the message to do what? P background child. We've received the vsync message, meaning it's time to paint. So I think we're doing a paint here of some kind, or we're doing a composite. I'm not sure. We do a thing whenever we receive vsync. We paint is what we do. We paint to the buffer, we create a drawing, and then we wait once the paint has gone through. So and then what else happens here? Reader mode is doing some stuff. It's checking on paint when waited for. It's checking the thing that was just painted to see whether or not we should be adding it to reader mode. And then we have this big block here where we're also just like waiting. We're polling. What are we polling for? Oh, this is basically the main loop. We've at this point, I suspect the test is over, and we've already like stopped we've recorded that the window has been opened, and we've stopped the stopwatch essentially, but we have to send a message up to the parent saying stop the profiler from sampling. And so that we don't react to that for another 34 milliseconds, is my suspicion. So all of this stuff might might not be interesting, but the stuff over here is what's interesting. And I think this is the big one again. I think this is the one we care about, and over here as well. Maybe there's some session history stuff that we care about. What's going on in here? We're importing some script, so all of this, like the tab content script's getting loaded up. Content session store is getting loaded up. Browser child takes by far the longest. So like this is the script stuff getting all loaded up in the child. And then what about these samples in here? What are you doing in here? Here, extension content. I'm not sure what that is, but let's drill down. Broker, some kind of, what is extension content.jsm? Whoa, that's a bug. This file handles the content process side of extensions. It mainly takes care of content script injection, content script APIs, and messaging. Who added this? Is this for web extensions? I think it is. Yeah, this is for web extensions. So we'll have some web extension stuff happens here. Some kind of broker is getting set up, I think. Okay, well, I think I've got enough information to start doing some experiments. I should check to see whether this tab progress listener thing is working properly. I should investigate the screen bound stuff because it looks like that's taking too long as well. I'm going to move this up here. I need to ensure, maybe see if getting rid of this browser init sync message is going to help. I suspect it will. I suspect getting rid of this will help a lot. And here's the thing, like when you remove something like this, whenever you get rid of it from the system, everything sort of shifts around. I mean, this is a very, non-determinism can be a real pain in the butt, and when you take a chunk like this out, it can shift lots of things around, and who knows how the system will behave, but I suspect things will just get faster if we get rid of the sync message. So I think I'm going to cap the video here. I think that's all I wanted to really explain. But that's what I'm going to be doing for this tpaint regression bug. If you're interested in following along with the progress, it's bug 1174770. And hopefully this video was useful. You got to see me kind of poke around inside a profile. All right, bye-bye.